Okay, welcome to this morning. Panos and Go ahead.
Thank you. When not all organizers are here, I would like to start by thanking the organizers for organizing this so efficiently. We had a lot of fun doing mathematics these days, so let's all thank them for their planning. So I had started the proof. I realized, I will remind you. So what we want, of course, is we want to prove this inequality, right? To relate the systole with the volume. And this part of the inequality we did last time, and now I'm in the middle of doing this part. But and we also said that. We also saw that this follows by this somewhat technical assumption. If the volume satisfies this, then the Gilson width is less than R. But now, what is the meaning of this? I realized I didn't even give a picture. What is the meaning of this, right? So what we try to prove is kind of obvious. So so just try to visualize it. So this is just a small number. So here we have that the volume of the ball of our manifold is much smaller than Euclidean volume, right? We have something that local is very small. So if you just try to visualize this, say you are in dimension 2, right? Let's just think in dimension 2. Well, you have a surface, and locally the volume is small. So how can the surface look like, right? It has to be something like that. It has to be thin, because if it has a thick part, the volume is going to be big. So here we look at balls, and of course, the ball here is very small, right? The volume of the ball. So if the volume of the ball is small, the surface has to be thin. That's all we are saying, okay? So
the just needed for some radius, yeah, not for almost.
Yeah, but locally, if you look at it, it has to be thin. Yeah, I'm not saying there is nothing to prove. There is something to prove, but I'm just saying that geometrically, intuitively, it's something very reasonable, okay? I don't want us to be lost in the formulas, so let's keep this picture in mind, but then we have to actually prove this, and as we know, even for surfaces, sometimes things are hard to prove. Okay.
So what you mean by this statement is that for every n, there exists some scale for which local volumes are small.
Well, actually, I could even fix the volume, but then I wouldn't get such a good constant, right? So yeah, this is a bit more technical, but I'm saying if you fix the scale, it's kind of obvious. And even without fixing the scale, it's going to work out, right? Because you see, maybe the picture is like that, right? At some scale is like that, and some other scale it's even much thinner, right? And I want to take advantage of this much thinner. So the thing is, the scale is much bigger always than the thinness. Okay, so having a small scale doesn't mean that I don't know anything. It just means that there is even thinner. Okay. Okay, so that was a calculation that this follows from that, and now and we did say that we are going to use separating subpolyhedra, so this is just an outline, and that's one of the somehow differences with other things, that we need to prove it for polyhedra, right? And the reason is when we chop a manifold into pieces, we need a polyhedron. We cannot chop it by a manifold. Okay, and now I gave a definition of what are these subpolyhedra, and maybe I should give a picture too. So let's say I am on the plane. Well, of course my things are compact, but it's easier to draw the picture on the plane. And I want something deseparating, so it's going to be something of dimension 1, and it might look something like that. Okay, it's like a grid, and of course you can draw this on a torus, the same picture. And deseparating just means that these connected components, the pieces here, fit in balls of radius D. Okay? So this is the object I'm looking at. Okay, and now there is this slight difficulty that maybe in compact spaces perhaps there is an argument to show that minimal such objects exist, but one doesn't really need to worry about this because as soon as my d-separating polyhedron is close to minimal, since I work with inequalities, it doesn't really matter. I mean, it will just be a pain to have some epsilons on the way, but I don't really need minimal. Okay, so delta minimal means it's delta close to the infimum, and every time I can pick delta to be smaller and smaller so that things work out. Okay, so that's okay. And then I showed this last time this lemma, so I can just do induction. So if I know that I have a d-separated polyhedron with unison with D, then the bigger space also has unison with D. Okay, so keep that and I'm going to reprove it. Okay, and now how the proof works again. So we have y, we have x, and we want to pass to y. But in order to pass to y, here I have this volume growth assumption. So here, that's the thing. Of course, it's easy to see that there is some polyhedron. You just chop the space in a lot of pieces, and then that's fine. But the problem is how to control the volume growth of y. Okay, the local volume growth of y. And I'm going to use the Koire inequality. So instead of writing volume everywhere, I'm just going to do absolute values, and sometimes I will remember the n, and sometimes when it's kind of obvious, I will not remember it, but I hope it's not going to be confusing, okay? So this is how I denote the volume. Okay, and of course, to bound the volume growth, I'm going to at some point use the Koire inequality, so I just start with a lemma. So I have a ball which satisfies this inequality, so the growth, the volume of the ball is less than some constant c r to the n plus 1. Then there is some lambda and an interval and a sphere of radius t that lies in this interval, such that the area of this, n minus 1 volume of this, is bound by this inequality, okay?
It's t to the n, not n minus 1.
Why? Here I had n plus 1, so here it's n.
Sorry.
Yeah, sorry. Right. Okay, and now this is just simply by Koire inequality. I just integrate. So I have my point. Well, I can approximate. I'm always in this business. It's convenient to approximate the distance function by a smooth function. Since you have all these inequalities that have epsilon, you can take the smooth function close enough to this so that you don't have problems. And by Sard's theorem, most of the level sets are rectifiable, and in fact, they are polyhedral, Riemannian polyhedral. Okay, so this is what we are doing now. And what we want to say is that if the inequality fails, right? So I have the ball and I look at the spheres in some range. I don't know yet what will be the range. This lambda is to be determined, but it will come out. So I want to say, oh, okay, it's not possible for all this to be big because I would have too much volume, okay? Which is reasonable. And now we just calculate by the Koire inequality. So we argue by contradiction. We assume that here we have this inequality, and then I get, well, I just integrate. Well, fortunately, this is easy to integrate. I integrate t. So I get this, and now if I pick lambda, so the question is how to pick lambda so that this works. And I pick lambda to be this. So now if I pick lambda to be this, I get, yeah. So note in this lemma too that every time I play this game, my epsilon drops, but it's always some positive number, okay? So that's why I have this here, so that the inequality works. So now if I just substitute this there, I get r to the n epsilon over 3 times 1 minus epsilon over 3. And if you calculate, you get like cr to the n minus 2 epsilon over 3 plus something, right? So you get that this is greater than cr n plus 1 minus 2 epsilon over 3 plus something small. So this is a contradiction, right? Because we know this is actually smaller than this. Okay.
But do you work with actual spheres or with this, or you first approximate the function? Then you
I approximate, yeah. I'm trying to cheat here.
Yeah.
So I said always just approximate the function, but this approximation, you know, it's going to distort this by very small. So this 2 epsilon over 3 will become, I don't know, 3 epsilon over 4 if I want, okay? So, but good question, yes.
Yeah. So is it possible for lambda, r, and t all to be arbitrarily small and b and s to be arbitrarily close to x?
Well, this is what worries. This will worry us at the end. Yes, a priori, yes. But then later, so this is the last step of the proof. Later, by using compactness, you show that, oh, okay, this doesn't happen. I mean, often compactness, you know, allows you to deal with this sort of problem. Okay? Right? Yeah, I mean, that's something that you could worry about, but this has nothing to do with my lemma, right? I mean, this lemma. Right? I mean, you are thinking about the last step of the proof.
Yeah, I'm just wondering what is the purpose of the ball and the sphere. If they can be arbitrarily small, how we are trying to use these things?
Well, I mean, the thing is, I do induction, and every time when I do induction, I would like my t to be at least bounded by what I had at the beginning. So if at the beginning, when I start the induction, I know that my integral doesn't go to 0, then throughout, I want to make sure that my interval doesn't go to 0, right? That it is controlled, okay? Right, that, yeah, I mean, the first step, I'm sure things are okay, then they will be okay throughout. Right? That's why I need this lambda. Yeah, it's a bit annoying that we have to make sure that it's bigger than lambda rather than anything, but it's easy. I mean, from the proof, definitely we get it easily, right? Okay. Okay, so now I'm going to use that to show that there are, well, existence is obvious, but there are disseparating polyhedra which also have this growth condition, okay? That's why. So lemma 2, which is closer to what we want to show, so assume that there are, we have a ball that satisfies, that has small growth at a point, right? And this is for a whole interval from tau to rho to r. Then there is a delta minimal R separating subpolyhedron that also satisfies this growth condition for some different interval. But again, there is a lower bound, right? Okay, so if for some t, I get this volume, then there is a rho such that in this interval, I have again this volume bound. So again, as you see, epsilon drops to epsilon over 6, but it's still some positive epsilon. Okay.
But this is already the main step. Yeah? So this is the
this is the main step. Yeah. I mean, but then later we'll have to worry a bit about this question. But this is the main step, because then I just apply induction and I'm done. Okay. Oops. Okay. So we argue by contradiction. So so what is my problem now? Yeah, maybe that's not completely useless. So again, what's my problem? I have my X, and I take my deseparating polyhedron, but maybe it has too much volume. It is deseparating, all right, but it has too much volume. So what do I want to do is I want to look at the sphere, so I know by hypothesis that it's going to be a small sphere around X at some range. And if this is too much, since the sphere is small, I will just replace this, the interior of this, by the red sphere, and then the volume growth improves by more than that, right? So I get a contradiction. So the thing, okay, so that's the argument. That's what we want to do by these inequalities. So this is my sphere that satisfies this inequality. And well, I remind you that I get it from this lemma, and I apply the lemma for C equals 2 to the n plus 1 factorial, and the T is the S here, right? Sorry. Okay, and now if we cut the part of Z inside S and replace with S, as I said before, we get another polyhedron, which is still deseparating because this S was smaller than this, so I didn't create a big connected component. And now I count the difference, right? So my hypothesis was that the volume of Z, I'm arguing again by contradiction, so my hypothesis is that the volume of Z is bigger than this, and now the volume of Z prime is smaller than this, so this difference is bigger than this number. Okay, and now I have to pick I have to pick my delta, so that delta is smaller than that. But delta I'm free to pick basically, and S. So here is where it is important that S was in a range. If S could be arbitrarily small, then I couldn't do anything, right? But since S is in a range, S is bigger than something, so I can just pick delta to be smaller than that something and get a contradiction. Okay, and I write the numbers, but so I will pick delta that small, and lambda was provided from lemma 1, and it is this, but yeah, maybe I don't want to bore you with explicit calculation. That's the whole point, right? Okay, so that shows that I can induct. Okay, so I start with this, and now we want to prove a theorem. So the base case, well, it's kind of obvious, right? If we have something of one dimension, and you say that the volume, yeah, so R is, so, yeah. I mean, when n is equal to 1, so for n is equal to 1, R is just whole xn. So R is equal to length, right? And xn, right, so the volume, so if the volume is, if the radius is bigger than r, so then I'm going to have an interval of length greater than 2r in x, right, which is a contradiction because we get too much volume for dimension 1. So this is obvious. And now we use lemma 2 and apply induction, except I have the problem that we discussed earlier, right? Which is that this t could go to 0, so I'm not having these bounds, right? So when I start, my t maybe is very small, right? I mean, it gets smaller and smaller and converges to 0, and I have none of these uniform constants that I was using throughout this proof, okay? But I claim that that's not a problem, because compactness will deal with this. So, okay, so what we need is, first of all, this to be smaller than epsilon, but we also need this tau, right? So we need both strictly smaller inequality, and also we need these two things. But I say both follow for compactness. So for every x, there is some t, right? The only problem is that maybe this t, right? So I take the supremum, for every x, I take the supremum such that this quotient is less than 2 over n factorial. And maybe t of xn goes to 0, right? But by compactness, I can pass to a subsequence, so xn I can assume converges to x. And then I have this for some fixed r, and this is strict inequality, right? While for bxn, I had 2 over n factorial, but I had something very small, so maybe I'll draw the picture. So this is something like what you do often with compactness. I have this x, and then I have this xn, and this xn has a very small ball here, and this x has this ball. But then if xn goes very close, I can just simply forget this ball, and the ball that I had for x also will work for xn, right? Okay, because remember, for xn I took the point is that I have strict inequality here. And if I go close enough, this volume of bxn tn is going to be nothing, 0, right? And then this is strict inequality, so I go close enough so that this strict inequality is going to help me and take the same radius for xn, basically. Okay? So that's the argument. I don't know, maybe you don't believe it, but that's the argument. Okay. So that's it. Okay, so that's, maybe we can think about it, but that tells me, so again, the point is that I have strict inequalities. With weak inequalities, this wouldn't work. But now, okay, so the second problem is this, right, this existence of epsilon, right? But then this function is continuous and is less than 2 over n factorial, and it's not, so where we pick the light r for each x, right? And so its minimum is strictly smaller than 2n factorial, right? Because we are again in a compact set, we have a continuous function in a compact set that is less than something. Well, the minimum is going to be less than something. So this epsilon here it is. Okay, so then I can do what I promised. So my proof works. Okay, so the last part again is by compactness. Okay, so maybe I will mention some open problems in this field, right? So as I said, I mean I mentioned them before, but I want to recap. The worst examples we have, so one difficulty is what happens as dimension goes to infinity. We would like to have an exact asymptotic bound, and there are examples for this. So certainly it cannot be bigger than that, but there is no worse example than that, and somehow this seems reasonable because tori or balls, if you like, it's just a calculation of how big is a ball in Euclidean space, and this calculation, you think, my space is going to grow more than Euclidean, and this calculation makes it very believable that this should be the better bound, but this inductive strategy, at every step of the induction, you miss a factor, so there is no chance to get it. So you would need a completely different proof. And another problem is we dealt with aspherical manifolds, but the problem of periodic geodesics, of course, makes sense for all manifolds. And the first interesting case seems to be the 3-sphere, because for the 2-sphere it's simply connected, but Krogh theorem does it for us. So this is another mystery. And finally, if we even start at dimension 2 and we say, okay, we want to have a global understanding of our manifolds, we have Buda's conjecture of surfaces. And another version of this is, now that we know Urison width, is whether the Urison width of any surface is bounded by square root of the area. Okay, so you want C independent of G, of course, right? C not dependent. Okay, so I have half an hour and I will maybe discuss some related, well, maybe I will discuss some background first. So first, I have my own proof of Krog's theorem, my own version of this. I mean, not written, but maybe I'll skip that because Rina explained. And I'll go to Fett-Lusternik's theorem. So this whole thing started, I mentioned this theorem that we know that always, so even in the sphere case, we know that there is a periodic geodesic and we want to give a bound. And now I would like to give a presentation. Well, I'm not going to actually talk a lot about, I'm not going to talk much about the actual proof, but I would like to point out that in fact, Fett-Lusternik's theorem works also in geodesic polyhedra, in geodesic metric space polyhedra, because the proofs that I know in the literature, they use analysis and they use manifold structure, right? And in fact, smooth structure on the manifold. But you don't need smooth structure, and you don't need analysis to prove this theorem. So I want to discuss it in this generality, but of course, if you don't have analysis, so I know Riemannian geometers are going to complain, there are no geodesics, right? Because you need the second derivative, you need something smooth, except that, well, we can redefine geodesics in a way that is consistent with the current definition for manifolds, right? So if I have a geodesic metric space, I'm going to say that something is a geodesic, so it could be closed, if for every x, there is some epsilon, such that there, this is distance minimizing. Okay, so I can always define length in a geodesic metric space. So remember, if I have a path in geodesic metric space, the way I define length is I take all subdivisions of the path, and I take the sum of these distances, and then I take the sum. So length is defined. There is a abstraction to define length. Okay, and now I say that something is a shortest path, right? If between x and y, the length of the path is equal to the distance xy. So now I'm defining geodesics to say locally they are shortest paths. Okay? And now this is equivalent to the Riemannian definition. One of the theorems you prove in Riemannian geometry when you study geodesics is that there are convex neighborhoods that locally these geodesics really realize the distance. Okay, so this generalization is not really, a proper generalization. It does work in Riemannian manifolds, but it just works in a wider range of spaces, okay? So I don't need, yes?
So if this is the definition of a geodesic, then what is a geodesic metric space?
Right. Well,
I just don't remember the definition.
Yeah, sure. No, I will tell you what's a geodesic metric space. But yeah, the only problem with my definition is that it's not consistent with the definition we give when we define geodesic metric space. But for this course, it was more appropriate. Okay, so I'm going to define geodesic metric space without using the word geodesic, which seems like cheating. So X, you're right, I should define a geodesic metric space. Let's go back and define it. So definition, if P is a path, then length of P is the sup of distance PTI, TI plus 1, PTI plus 1, over all partitions, what I said before. 1, and now 2, P is the shortest path. So this is, so I'm not calling it geodesic anymore, that's what I'm doing. So P is the shortest path if between A equals P0 and P equals P1, if length of P is equal distance AB. And 3, X is geodesic metric space if for every AB there exists shortest path P from 0, 1 to x, P of 0a such that P of 0a and P of 1 is equal to B. Okay? Yeah.
For the definition of length, are we supposed to add up over these distances?
Oh, sorry, yes. Sorry, yes, sorry. Okay, so this is how we define. I mean, in the literature, this shortest part we call it geodesic, but I don't want to call it geodesic. That's why we call it geodesic metric space, because I want to call geodesic a local geodesic, because this is the same what we mean in Riemannian geometry. Okay, this is equivalent. So I can make sense of this. Okay. And now, okay, I'm not going to really prove it for all geodesic metric spaces. I'm going to say that the space X is locally uniquely geodesic if, whenever 2 points are very close, so there is some epsilon, so my spaces are compact here, there is an epsilon such that if the points are a distance less than epsilon, then they can be joined by a unique shortest path. Okay, so geometrically unique. I mean, of course, you can deparameterize. Okay, so when they are close, so this is the condition of manifold. So this is, and of course, this is also true for manifold. So you see, I mean, if you have a sphere, say, you have two geodesics, of course, this one and this one, by unique shortest path. Okay, so this other path is not shortest. So here the shortest path is unique. Okay, so it's not a geodesic, it's really more than a geodesic, it's the shortest path. Okay? So this is stronger than geodesic. Okay. So a nice example of spaces that are locally unique to geodesic are cut K spaces. But cut K spaces are not smooth, right? And I don't know how much analysis you can do on them. And of course, we can give, right, so for example, I mean, you can take a sphere, I guess, and take a hemisphere, and I identified it along here, and this will be cut K. So it's going to be a singular space, but not a manifold. Okay, and now the theorem is we have compact locally uniquely geodesic metric space with pi n non-zero, then X contains a periodic geodesic. Okay, so maybe some comment on, so this, or maybe it is the other comment, yes. So this, if I take two equilateral triangles and I join them, this is not locally uniquely geodesic. This point gives a strap, right? So we don't have locally unique geodesic space. While if I thicken, I do my triangles to be part of a sphere and I identify, then this is locally uniquely geodesic. Okay, so it can be singular, so to speak, but we have to have some condition to get the local. And now this problem, this of course, we don't know if here there is a periodic geodesic, is equivalent to the famous problem of billiards, right? If triangular billiard have closed trajectories. Okay, so this is very hard, but this is easy. The second one, this we can do, but this we cannot do. And now the proof, we don't do anything new. Actually, we apply Birkhoff shortening. We know that Birkhoff shortening can be applied here. Well, there is this analysis you use to show that the min max is a geodesic, but this analysis is just replaced by a geodesic lemma, that if we have convergence of small geodesic segments, they convert to geodesic, right? So it's just a purely geometric remark that allows us to apply basically the same strategy, but prove it without analysis and for complexes rather than manifolds and so on. Cut K spaces, but it's again Birkhoff shortening trick. And now, but there is a question which I find surprising. So it's known that if you have a manifold, right, if I have a sphere, then there is actually a simple periodic geodesic. Okay, but now let's say I forget my analysis and I do cut K, or even worse, do just geodesic. Can I show that there is a simple periodic geodesic? For some reason, I mean, there are the standard proofs, but we tried to apply them and we didn't. I mean, the Haas-Scott flow, we tried to use the Haas-Scott flow, but we couldn't do it. And so here is a question. Maybe it's not a hard question, but yeah, something that is known in the smooth case, but it's not known when you. Okay. Any questions? Well, I guess I'm not going into this. I mean, I will only point out if you are interested in this and you have never looked at Doccarmo, this is a short paper, 3 pages long, that has no background. Okay? Yes?
Do I understand right that periodic geodesic on a metric space is when we can like extend to a periodic curve our initial geodesic on the segment?
A periodic geodesic is just an image of S1, right?
Okay.
That's my definition of periodic geodesic, just an image of S1, which is a geodesic, okay? A homeomorphic image of S1 that is a geodesic. Okay, so I thought I would state this question. And, okay, and now, as I said, I'm going to talk a bit about coarse analogs of unison width, and the coarse analog is, one coarse analog is asymptotic dimension. So some of these problems have somehow affinities with questions in coarse geometry. And I will start with one where there is an obvious somehow analogy. So, but let me first define the asymptotic dimension. So this is similar to our definition of width via covers. So asymptotic, the dimension is less or equal to, that's wrong. So it's less or equal to n if for every d there is n in the cover, such that the sets of diameter, we have sets of diameter less or equal to n, so they're like that. So the diameter is bounded. And any d ball intersects at most n plus 1. So this is the UIs here. And my condition is that I have a bounded multiplicity for d balls, so for smaller balls. So imagine d is smaller than n, right? So for every d, there exists n, which is n of d, such that, etc. Okay, and here I'm imagining d getting bigger and bigger. So when I get d bigger, I still want to find some bigger n where it works. Right? So the problem is, if it holds for a bigger d, it holds for a smaller d. So the question is, what happens as d goes to infinity? Okay, so instead of looking locally, we look at infinity. And this is how this is defined. And maybe it's more instructive. Oops, yeah. Okay, so maybe, So maybe I will give some examples. Well, R is maybe the easier case. You take this, and now you pick T, and you say, okay, I'm going to take intervals of length, I don't know, 2D, and have them intersect like that. So you see that the multiplicity, the d-multiplicity of the cover, so this is U1, U2, the worst can happen, my ball can be here, so the d-multiplicity of the cover, well, I call d-multiplicity how many the ball intersects, is less or equal to 2, so as d is less or equal to 1. And you usually see that 0. Okay, and now I can do something similar for R2, except my cover is going to be more interesting, so I'm going to do, I'm going to take stripes, like that, but I'm not going to match them. I'm going to match like that. And now if I take a ball, the worst it can happen, because the size of the tiles are much bigger than my D. If I take a ball, the worst can happen, it can hit 3, right? So asymptotic dimension is less or equal to 2. Another interesting example is a tree where, so maybe, okay, so as the tree, maybe this is a good exercise if you want to get a feeling. The problem here in the tree case is that your pieces are not going to be connected, but I never said they should be connected. Okay. So here's a theorem that actually has the same proof as the previous theorem. If I have a connected graph with growth function gamma r, where the growth is smaller than Euclidean, then the asymptotic dimension is at most k. Okay, so it was known before, maybe we'll see this paper later, by work of graph theorists actually, that and using some embedding results in graph theory, that this asymptotic dimension is finite, but this gives a finer bound. And the idea is kind of the same. You do induction, right? So you do the Coeri inequality, if you like. So you pick a point and you look at the spheres, and now the spheres have small growth, and so you can find nice covers for the spheres, and you go down. So it is by induction. The same in a way, very similar. Just things go to infinity and quantifiers and so on, but it's a very similar result. So there is really analogy. In this case, it's kind of identical or very close, the Urison width case. Okay, so another result. So there was a question there whether, in my paper, whether Ricci less or equal to 0 implies that the asymptotic dimension is less than n. Of course, when you have Ricci less than 0, you have the growth condition, but you don't have local control. I mean, you don't have bounded geometry.
You mean larger than 0? Ricci should be larger.
Oh, sorry. Yeah, greater or equal. Thanks. Yeah. So greater or equal to 0. Thanks. Otherwise, it doesn't make sense. Okay. So this implies that the growth is small, but you don't have bounded geometry. So if you have bounded geometry, a bounded geometry manifold can be approximated by graph. But if you don't have bounded geometry, you cannot approximate by graph, so it doesn't follow automatically, but it is still true. However, there is still something that is unknown in this case, is whether the asymptotic dimension, so this is still open, for this, right, is asymptotic dimension n equivalent to growth r to the n. Okay? So it, of course, it's easy to see when you have bounded geometry. Okay. Oh, here I had my examples, fine. Okay, so something else about the asymptotic dimension. The asymptotic dimension of the hyperbolic space is n, so no surprise, and the proof is similar to Rn case. I mean, I did R2, but Rn works like that. However, it's even unknown what happens if you have strictly negative curvature, but you don't have a bound, both upper and lower bound. You don't have lower bound, and your manifold is like Hn, homomorphic to Rn. Right? It's not clear, it's not known whether the asymptotic dimension is even finite. For manifolds with the co-compact axion, everything is fine. It's exactly what you expect. Okay, the asymptotic dimension. But for complete manifolds where you don't have a bound, it's not known even that it is finite. While the Urison width, if you like, is of course the n Urison. The Urison width is finite. It's n. Right? I mean, it's the macroscopic dimension.
Can I ask a question?
Yeah.
So in your theorem, asymptotic dimension is bounded above by k, but do we know that k is achieved or k is there is some other dimension that is achieved? Do we know?
Well, I mean, in this generality, yes, because just take Euclidean space or a lattice in the Euclidean space, it has the asymptotic dimension exactly. Okay. So yes,
And
it is
strictly
optimal.
less. Strictly less is also so. are there spaces where asymptotic dimension is strictly less than k? So the growth is, I guess my question is growth is.
Okay. If you can have, I mean, if you can have exactly, let's see, what was the theorem? Right. So if this, then asymptotic dimension is so you mean if the growth is, say, r to the k? Well, yeah, I can make.
Maybe we can slice the space to.
Well, I'm not still sure how to formulate the question, so that's what I'm thinking. I mean, if you. So what is the question exactly? That's what I'm trying to think.
The question is this limit for some k is 0.
Right.
And the conclusion is asymptotic dimension is less than or equal to k.
Right.
Let's say k was 2. So the question is, for this space, we know the upper bound of asymptotic dimension, but can asymptotic dimension 1 be achieved?
So I have, let me just try, so let's do an example, as you said. So I have limit of gamma r over r square equals 0. Well, of course I can have a line, right?
R cube.
Okay,
Yes.
gamma r over r cube is equal to 0. Then the asymptotic dimension is like, I mean, the thing is, I just have a limit here, right? So this can be like a line. So a line satisfies this. So the asymptotic dimension could be 1, could be 2, could be 3, could be all these three values. Okay?
Okay.
Can I ask? So
Yes.
for the same problem, so if the growth rate is like r to the power of q, where q is not an integer, so is there a situation where you can say what the asymptotic dimension is?
Well, it's always an integer asymptotic dimension. So if it falls, it's a bit surprising. It's kind of sharp. If it falls below if your integer is below k plus 1, then the asymptotic dimension drops down and it's k. Probably, I mean, so the thing is, the way you define growth is you take the supremum over the growth everywhere, right? So it's likely, even though I cannot guarantee it right now, it's likely that somewhere you're going to have big growth, right? You won't be able to achieve. Right? Yeah. The thing is, if you fall below, so it's a bit surprising, right? If you fall a little below k plus 1, you already, If you fall a little below it, the dimension drops by 1. But you're right. I mean, does this mean that actually at some places the growth is big? I'm not sure right now, right? Because it's not clear that we can achieve, but we should be able to achieve. It's not so clear we can achieve any. We should be able to do that. Anyway, well, this is okay. So as I said, for Vinci positive, we can still ask a question. This is still not known. And okay, so let me give some other coarse analogs. So let's go to the Ziegler constant. So Ziegler constant was studied both by graph theorists, computer scientists, and geometers under different guises, right? So this separator theorem is used all the time for algorithms, in computer science, and so on. But what it says, basically, it's the same. It's very similar to Hershey's bound for the Ziegler constant of the sphere, right? So what is a separator theorem? It says that if I have a graph with many vertices, well, there are, I guess, different versions, then you can separate a big piece of the graph by c square root v vertices, right? So this is the separation. So separates means, well, both pieces have, say, greater than v over 3 vertices. Okay? Like that. So, yeah?
Under what assumptions?
for planar graphs, right? For any planar graph, that's the only assumption. So it's like, so that's why I say it's analog to HS2. Okay? So now this might not seem very interesting, but here is another theorem where computer scientists do more geometry than geometers. It's a Pareto theorem for non-planar graphs. So to begin with, so what are these non-planar graphs? Is minor restricted graphs. So this just means minor restricted. Here there is no kn minor for some n. So the minor is like, it's not exactly this. It's like having a subgraph, so this is, let's say, K4. So maybe this is subdivided. So this is the no K4. This is not contained in my graph, right? And I can define it for Kn. Now, if you have a surface, there is a bound to the complexity of the graph you can put in there. So this is the graphs that go in a surface are minor restricted. So if the hypothesis here, where if a graph doesn't embed in a surface, then there is a bound of a fixed genus, ST, then there is a bound of the Ziegler constant. It could be the Yang-Yao theorem. Okay? It would be exactly Yang-Yao theorem. But this is stronger than Yang-Yao, so it's a generalization because this is not equivalent, right? So this class of minor restricted graphs is more general than non-embeddable graphs or fixed n, right? So for example, if you take a grid, right, and you take a point and you join the point to every point in the grid, this is a nice graph, but it doesn't embed in any surface. Okay, this is not, it is minor restricted. It doesn't contain every k in the subgraph. But it satisfies this separator theorem.
Just to clarify, so non-planar means it has a kn minor.
Okay, non-planar is bad terminology, so I'm going to correct the type. Minor. So I say minor, imagine it as a subgraph. I mean, it's almost flat. Okay?
For some n, yeah.
For some n, yeah. I mean, it's like for some n, for a fixed n, yes.
What is the conclusion? So the separator has at most
constant square root, so the constant depends on n, square root v, so the same conclusion as Yang-Yao, or yeah, thanks actually, because that's the sense the way I stated it. Right, so this is a theorem. I mean, in some paper, Gromov says that it would be good if geometers came up with a geometric proof of that, and I thought that's the right place to say this. Strangely, and now this is another interesting theory, the theory of minor restricted graph. It's a very rich theory, so I think Seymour and Thomas have written 20 papers on this, of a total of more than 500 pages, so it's a huge thing. And they are important in graph theory and computer sciences because they are kind of the opposite of expanders. Expanders is the jungle, right, is the wilderness, while here is civilization, graphs where we can do something. We can say something, and we can say a lot of things. For example, we can say this, but there are a lot of theorems, and I'm going to give in the last minutes one more theorem about these graphs. So I will go back to asymptotic dimension, and if we take a planar graph or a Riemannian plane, then asymptotic dimension is less than 3. Right? So we didn't know that. Actually, they don't have Rosenberg, I think. I don't have the reference, but before us, there was a bound of the asymptotic dimension of planar graphs, which was 63, and it used some important classical result in computer science. Okay? So computer science, for some reason, implicitly, they are interested, sometimes explicitly. There are papers where they are interested in asymptotic dimension, except this D and N, they wanted to have some relationship. Okay? And of course, these things you can make sense for them even for finite graphs. Okay, so, but this is a wrong theorem, right? The plane has dimension 2, and a couple of other people noticed that was not the right theorem. So Jorgensen and Lang proved that it can be improved in 2, and some other group of people also improved it to 2. In fact, they used the same proof as us, but they used also another result that before our work.
Does Nagata dimension? Is it the same?
Yes, actually, and this follows too. Yeah, Nagata dimension is the same, and also will be the same for the next theorem that I'm going to state that now.
I just don't know the definition.
Yeah, no, I mean, Nagata dimension is not. Okay, so you ask what is the definition?
I mean, is it like similar to asymptotic or?
Yeah, okay, no, it's very easy to define, at least asymptotic Nagata. So there are different terms.
Okay.
So I will give you asymptotic Nagata. So you remember we had D, this ball D, and then we had N. So the UIs could be huge, right? They just had to be bounded, okay? But in the definition, you ask that the diameter of the UIs is smaller than K times D, okay? For some, so they're allowed to be bigger than D, but not much bigger. They have to be at a fixed scale bigger, and then you get asymptotic Nagata.
So it's a weak notion. Yeah? No.
It's stronger. Stronger because you ask more. Okay, so as I said, Jorgensen and Lang did that, and in fact also applied it to calculate, to give a bound for the asymptotic dimension of three-dimensional non-positively curved manifolds. So in dimension 3, there is no wild examples, as I was talking before. But also this group of group theories and computer science.
If it's like very negatively curved with no lower bound.
Yeah, dimension 3 is fine. Yeah, we can apply this theorem and they're done. So you have to go above dimension 3 for counter examples. And now this group, I mean, it's 7, 8 authors, I don't remember, so there's 6, so I didn't list the authors. They also proved it, but they did something better. I mean, we had conjectured in this paper that for planar graphs and even for minor restricted graphs, the asymptotic dimension should be at most 2. And these people proved it using this theory, right? So I don't know how to prove this. I mean, without the 500 pages of Seymour and Thomas, that's a very geometric theorem, right? We should know how to prove it. But I don't know a geometric proof that we could understand. The proof is long, technical.
But what's the statement?
The statement is that asymptotic dimension, it's the same. So first of all, this is 2. So the statement of their theorem is the following, that this is 2, and this does not contain KL. And this is not the author's.
So usually when people study like a study planar graphs, like there's also this K33 graph minor that is also a problem, but that it doesn't matter here at all.
No, it doesn't matter because if you don't allow K10, right, then you cannot have K33.
Right.
Okay, so yeah, I mean, you can talk about more refined things, but yeah, I mean, for this purpose, this Kn is all that we care about. Okay.
But if you just fix, like, you don't have K5, then Lipton-Daryan holds apparently from what you said, right? So for Lipton-Daryan, you only need that there is no K5, you don't need K3.
Right. Yeah. But so this is very general, right? I mean, the asymptotic dimension is always 2. Okay. At most 2. And of course, there is an open question. I mean, does this theory have a coarse analog? Right? So, for example, you can say, okay, instead of not allowing Kn, because we are geometers, we don't want to allow coarse Kn. So we have these graphs, and maybe there are Kns, but at some point they are thin, right? Okay. So doesn't have a theory. So in some cases, one knows that if you don't have a coarse Kn, then you are quasi-symmetric with something that doesn't have ki, but this is not true in general, so you cannot get it for free, so to speak. But in some cases it's true, actually. So for example, for trees, I mean, something is a tree if and only if it doesn't have a k2, a cos k2. Anyway,